Well, I want to thank President Albrecht for inviting me this morning and giving me the opportunity to tell you about the Space Dynamics Lab and the WISE mission. Let me get our projector working. WISE, again, is the Wide Field Infrared Survey Explorer, whose mission was to map the complete universe in infrared light. Now, to tell you the story about WISE, I want to start a few years back. Actually, let's start about 430 years back in 1572. In November 1572, a bright star appeared in the sky where none had been seen before. It was in the constellation Cassiopeia, which many of you may know as the Lazy W, and it was actually bright enough to be seen during the day. We call it Tycho's supernova after the famous observer who recorded his observations of Tycho. Of the supernova. After a few months, it started to fade, and for the last 430 odd years, this is what you've seen if you looked at that part of the sky. That's exactly what you see if you went out tonight and looked at that part of the sky. The supernova faded to the point where it was no longer visible. But a few months ago, the WISE instrument built at Utah State University took a look at this chunk of the sky, and this is the image that it returned. That red ball you see is the remnants of the supernova, the gaseous remnants of the supernova traveling outward from the original burst at 10,000 miles an hour, and they've been traveling outward for 430 years. They're far too cool to be seen in visible light, but the WISE instrument is sensitive enough to see the remnants 430 years after the event. Now, supernova are some of the types of phenomena which physicists study to understand our universe. Now, WISE was a NASA mission, and part of NASA's mandate is to understand the origins of our universe and the processes that form our universe. Back in 1998, knowing how important seeing things in infrared is, as you just saw in that photo, a bunch of scientists began discussion of the need for an all-sky infrared survey. In 2002, a proposal was made to the Jet Propulsion Laboratory of Caltech, which is almost an arm of NASA, to fly an all-sky mission, and SDL was a partner on that proposal to build the science instrument. We built the actual instrument that takes the pictures. Funding began in 2004. We actually launched December of 2009, a little over a year ago, and the mission does come to an end at the end of this month. So, why WISE? Why do we call it WISE? First place, it's wide field. Wide field means the opposite of your pocket camera where you zoom into something. Wide field's the opposite. Zoom out and you see a lot of the sky in a single picture. Infrared, and you'll see many examples. In addition to the Tycho supernova, you'll see many examples of why we want to look in the infrared. It's a survey. That means that we're not, unlike a Hubble, for example, we're not going up and pointing at certain objects to look at particular objects. We're surveying the whole sky in a systematic pattern. And it's a NASA Explorer class mission, which, of course, makes a great acronym for the program as well. So a quick overview of the instrument. It's got a 40-centimeter telescope. That's 16 inches. Pretty modest-sized telescope by today's standards. It's got 4 cameras. All 4 cameras look in infrared light, 4 different colors of infrared light. But when we take a picture with those 4 cameras, all 4 are looking at exactly the same spot in the sky. But they're looking in 4 different colors, 4 different infrared colors that we can't see with our eyes. The unique thing about the WISE instrument is it operates very cold, minus 430 degrees Fahrenheit approximately. And the reason is pretty simple. Our cameras are looking at infrared light, which is heat. You can sense heat yourself, not with your eyes. Your eyes can't see infrared light, but you can sense infrared light if you walk outside on a sunny day and you feel the sun on your skin. You're sensing infrared light with your skin. WISE's cameras are sensitive to infrared light or heat, and if they were warm, they would blind themselves. Their own heat would blind them. So we have to keep the cameras very cold in order to take the pictures in the infrared. So let's talk about a little bit about the science that WISE hoped and has in fact accomplished. In the process of doing this all-sky survey, we expected to find hundreds of thousands of asteroids, many that had never been seen before, for the simple reason that asteroids happen to be much brighter, emit much more light in infrared than in visible. We expected to find quite a number of brown dwarfs. Brown dwarfs are very cool stars. They're stars that are so cool, in fact, they don't emit any visible light. So all the big instruments on the ground and the Hubbles and so forth can't find them because they don't emit visible light. But they do emit infrared light, and WISE expected to find a number of brown dwarfs. We may actually find a brown dwarf type star that's closer to our own solar system than any other known star previously. Currently, the previously known closest star is Proxima Centauri. And a couple other things WISE should find in its survey are galaxy clusters and ultraluminous galaxies, which are some of the most distant objects in the universe, and ultraluminous infrared galaxies are some of the brightest infrared objects in the universe. So why did we have to build a new instrument to do this? Well, here's a single image from the WISE instrument, and you can see it. The moon there gives you a perspective of the scale. It's pretty, as far as astronomical instruments go, it's a wide field of view. It takes a big picture. If you tried to do such a survey, and it takes 6 months to cover the sky taking pictures of that size. If you tried to do a all-sky survey with an instrument such as Spitzer is another infrared telescope that's currently up in space taking pictures, but it has a much smaller field of view, as you can see by this green box right here. If you tried to survey the whole sky with that size of field of view, it would take you 38 years to do it. And just as another example, if you tried to do the job with Hubble, which has an even smaller field of view, it would take you 177 years to do it. So even though Hubble's been up there many, many years taking pictures, it hasn't even scratched the sky in terms of covering everything that's up there. And again, I already mentioned infrared. Here's another example of the difference of what you see in visible and infrared, an example that is maybe closer to home. This is a picture of our principal investigator by the name of Ned Wright down at UCLA. You can see the typical visible picture, but look how dramatically different the infrared picture is. The features that come out and the features that are dark are completely different, which is why it's so you can see things in infrared that you can't see by looking in visible. You might also ask, it's very expensive to get to space. Do an infrared survey, why don't you do it from ground? Well, here's what you walk out at night, look at a particular point in the sky, here's what you see with your visible, sensitive eyes. But if your eyes were sensitive to infrared, this is what you would see. The atmosphere is opaque to infrared light. We can't see through it. Not only can we not see through the atmosphere, you'll notice I painted that white and not black. The atmosphere itself is so warm that if WISE were to try to look through it, it would blind the instrument. It is so hot in the infrared, it's too bright it would actually blind us. So, next thing we had to do was design a mission in some systematic way to survey the complete sky. So here's WISE orbiting Earth, not to scale as you can imagine. Notice that WISE is pointing away from Earth. As WISE orbits, it always looks directly away from Earth. Now let's zoom out way away from space and try to imagine where the photograph that WISE is taking would be. So there's one picture. It takes 11 seconds for WISE to take that picture. But in that 11 seconds, WISE is orbiting and it's moving. So by the time it gets to the second picture, it's in a new place in the sky. Now it overlaps the first picture by about 10%, but then consecutive pictures continue as we orbit the Earth and we create this ring of photographs in one orbit. But then we continue orbiting, and the next ring of photographs almost overlaps the first ring. It overlaps by 90%. You can't tell from this, but you'll see in the animation in just a moment how that ring is changing direction slowly as through the seasons. As we go around the sun, that ring revolves as well. And after 6 months, that ring of photographs has gone 180 degrees, which actually covers the whole sky. So in 6 months, in this constantly taking pictures in this orbit, we cover the whole sky. Now, it takes a lot to fly a space mission, much more than just the science instrument. I happen to think at SDL we're lucky we get the fun part, building the science instrument, but it does take all the rest of these pieces to get up into space. You need a launcher, a launch vehicle. We flew on what's called a Delta II launcher. That's actually a photo of our launch down at the launch site the night before we launched. You can see our little WISE science instrument here that was built up in Logan. But we're just a science instrument. We had to have someone help us, give us power and transmit our data down, and that's called the spacecraft. You can see the spacecraft is here with solar panels to give us power from the sun, and a big antenna here to transmit our data down. Just by chance, not by chance, by design, WISE doesn't send its data to the ground. In fact, it sends its data over to another satellite called TDRS, which then transmits our data down to the White Sands ground terminal. From Light Sands, the data gets distributed to all of the science community that processes the data. So, as we've said, we built the WISE most technical slide I think I have here. So, this is a cross-section of the WISE instrument. You can see right here is our little telescope, 16 inches in diameter. Down here are our detectors, or our focal planes, or cameras, whatever word you'd like, are down here at the bottom of the telescope. The light comes in through the top, bounces through 13 mirrors, and comes down to the cameras. Now remember, we have to keep it cold. So the easiest way to keep it cold is just the same thing you do with a drink. You put it in a thermos bottle. And this big assembly is essentially a giant thermos bottle. We have to have a lid on it to keep it cold while we're on the ground, and after we got to space, we ejected the lid, of course. And then just like your drink, you need ice cubes to get cold in the first place. Well, we have 2 ice cubes on board. We have 2 big hydrogen tanks here. There's one here, a bigger one, and a little bit smaller one here. They're shaped like donuts, so you can just see parts of them in the cross-section. Before we launched, we filled those tanks with hydrogen, liquid hydrogen, and then we froze it. And then as the frozen hydrogen melted over about 7 months, it kept us cold, just like your ice cubes in your drink in a thermos bottle. So the ice cubes lasted for 7 months. We actually ran out of cryogen around July of last year. But the thermos bottle is so good, the cryostat, that we've only been warming up very slowly since then. And in fact, we're still operating and taking pictures today, even though we have warmed up from the coldest temperatures. So here's some photographs of some of the pieces. This shows one of the 4 cameras in the WISE instrument. Now, you would think for $2 million a piece, you'd get at least a lens or something with it, but you don't. For $2 million, you get nothing but a bare focal plane. This is the actual telescope, WISE telescope, before it was installed into the cryostat. This is one of the cameras bolted to the back of the telescope. There were still 3 more to bolt on. And then this is the fully assembled WISE instrument looking down, and you can see the mirror, the telescope main mirror right there, the gold mirror there. After you build an instrument such as WISE, you have to make sure it's going to survive the ride to outer space. It's a rough ride, and it's a loud ride. So you test it before you put it onto the launch vehicle. You put it onto a big shake table and you shake it. Basically, you shake it to the same level you expect to see when you launch and make sure that nothing breaks. Then you put it into this big chamber and you radiate it with radio waves. What you don't want to happen when you get to space is we're sitting here orbiting Earth and Dish Network satellite passes over our head. We don't want to see I Love Lucy on our focal planes. We got to make sure that their radio transmissions through us don't affect the quality of our data. So that's what the test here is. Not only is a ride to space very rough, it's also extremely loud, excruciatingly loud. So if you want to test for that, of course, the best way to get excruciatingly loud noise is to hire the local punk rock band to come in. Well, we didn't hire the punk rock band, but we did hire their roadies to bring in their speakers to surround our instrument with these stacks of speakers. You notice the man down here in the corner gives you an idea of the size of the speaker stacks. And then we subject it to this tremendous levels of noise to make sure that the noise inside the fairing during launch doesn't break anything. Once you've done all that testing, you know you're good to go for flight. You got one more step before you can actually go to outer space. You have to do what we call calibration. Calibration is the process of showing WISE a light source that you know exactly how bright it is because we're in a laboratory and we created the light source, and recording what WISE says about that light source, what kind of reading you get out. Then when you get up to outer space and you see a star and WISE is giving you these readings out about the brightness of the star, you know how bright it is because you've looked at different sources to correlate those readings to brightness levels. That's the process of calibration. It's actually a long and involved, it took many months in the laboratory setting here. You can see WISE here looking through all of our calibration equipment and all the additional equipment it took to keep it cold. Of course, it won't work if it's not cold. They had to have it cold during this period, during the calibration process. So finally, WISE is ready to ship. It's all been assembled, tested, and calibrated. This photo was taken actually just a few days before we shipped it out of the lab. A couple more steps before you get to orbit. First thing you got to do is take our science instrument that was built at USU, and you need to bolt it to the satellite. Here's a photo of the actual satellite we had. This is the solar panel that provides power. This is all the electronics and the radio transmitters. There's an antenna on this side. This was right before we started to package it up to put it onto the rocket. Once you have it all bolted together and tested, the next thing you do is you put it onto the rocket. Very early one morning down at Vandenberg Air Force Base, they put us into this can to keep us clean, and lifted us up to the top of this mobile service tower. Inside the mobile service tower is the Delta II booster. So they lifted us up in this can, took us inside, and set us down. This picture is taken inside that same mobile service tower. So now the top of the Delta II booster, you can see that white cone is the top of the second stage of the booster. And we actually separated on orbit right here. And there we are sitting inside. Half of the fairing is in place. And after this picture is taken, of course, the other half of the fairing was put in place. Finally, after 4.5 years of work and almost 12 years of planning for the process, on this 6:09 a.m. on December 14th of last year, we launched. But we had a cover on, so we couldn't see anything. It actually took 2 weeks of checkout on orbit before we were ready to kick the cover off and say, okay, let's see how well this instrument's going to work. December 29th, we kicked the cover off and got our first light image. That image is, not only is it a pretty image, but it was critical to our knowledge of how well the instrument worked, and it told us a lot. It told us that the instrument was working. All 4 focal planes were giving us good data. Most importantly, that it was in focus. There's no focus mechanism on WISE. If it had somehow gone out of focus, there was no way to fix it. So we were, needless to say, very, very pleased to see this picture. Now, I'm showing you a picture of an instrument that takes pictures in infrared light. I'm showing you the picture, and you can see it. Obviously, I'm not showing it to you in infrared light. If I did, you'd see nothing but black up there. So how is it that I take these pictures that are taken in infrared and convert them to something that you can see invisible? Well, here's how we do it. This, I guess I did have a second technical slide. This is the electromagnetic spectrum. At one extreme, you've got X-rays, all the way through this tiny chunk here in the middle with visible, and all the way out here to radio waves. And of course, human eyes are only sensitive to this little tiny chunk of visible light in the electromagnetic spectrum. WISE is way out here. WISE has 4 cameras, 1, 2, 3, and 4, and I showed them as sort of modeled because I can't show. There's no way. The idea of saying this is an infrared color has no meaning. We can't see those colors, but that's where the bands exist, are sensitive to light in this region, which we cannot see. So in order to take the pictures that WISE returns that we can't see and convert them to something you can see, we simply do something called false coloring. We take the data that band 1 returns and we show it to you as blue. We take the data that band 2 returns and show it to you as cyan. And likewise for 3 and 4, we show as green and red. And that's how we convert these infrared pictures into something human beings can see. So as an example, this is band 1. This is an artifact of the projector, unfortunately. This should be black and white. That's what the picture looks like before it was false colored, or would look like it if it were black and white on the screen. And then we take it and we convert it to a blue color. Same with band 2. Again, this is a black and white picture. The bright spots show where it's gotten more energy, and the dark spots show where it's got less energy at that infrared wavelength. And we color band 2 as cyan. Now, as I go through the bands 3 and 4, watch how much different things you see, although all 4 of these pictures are taken at exactly the same exposure. So here's band 3 in green and band 4 in red. As you can see, what you see in those 4 different colors is not only, you can't see it as human beings, but it varies dramatically across those 4 colors. And when you combine them all, you get the composite picture that we publish. So let's look at how WISE compares to looking at the sky with previous surveys or in different colors. You've seen some images already. Here's a simple visible image of this night sky at a certain point in time, exactly what you'd see if you went out with a pair of binoculars and looked at that point of the sky with your own eyes. The exact same spot looks like this from WISE. Again, this is a bigger picture of the Tycho supernova, but you'll notice how many things are visible in the infrared that simply aren't visible and can't be seen invisible. And again, that's why the scientists wanted to fly a mission that was sensitive to the infrared. Now, WISE is not the first all-sky infrared survey. There was an infrared survey done by an instrument called IRAS in 1983, almost 30 years ago now. And the IRAS all-sky catalog has been a mainstay of astrophysics research for 30 years. This is an image from IRAS, but as everyone knows, anyone who uses a computer certainly knows, or a cell phone, technology is advanced. Here's the same spot of the sky as seen by WISE. The astrophysics community is ecstatic with the data that WISE has returned, and this picture tells you why. Because they have used this IRAS catalog, which was an excellent product in its day, but is simply not up to snuff anymore. And WISE is the replacement. WISE will be used for decades to come because of the quality of this data. Let's just look at some pictures that we've taken around the universe. I'm going to start close to our own solar system. We've seen a lot of comets. This is Comet Siding Spring, named after the Australian observatory that first saw it. Comet WISE. This is actually the first Comet WISE that now has 16 siblings. We've now found 17 comets discovered by WISE. Asteroids. This little illustration shows 4 consecutive pictures at the same place in the sky from 4 consecutive orbits, an hour and a half apart. Take a picture, an hour and a half later, take a picture, do it 4 times. The orbit's progressing slightly so that the pictures don't perfectly overlap, but they overlap to a large degree. There are a couple stable things in those pictures. You see those 2 bright stars right there aren't moving. But you look at all the red dots that move frame to frame, and what you're seeing is asteroids. As a matter of fact, when things move frame to frame, that's how we detect the asteroids, is by looking for things that move from frame to frame. Now, if you could fly up above our solar system and look for where all the asteroids might be, this is a cartoon showing what you might see. Here's the Earth's orbit, Mars' orbit. There's a main belt of asteroids between Mars and Jupiter. That's called the main asteroid belt. There's a couple other families, a bunch called the Trojans that follow Jupiter in its orbit, and a bunch called the Greeks that lead Jupiter in its orbit. So this is what an artist's conception of what you would see. Here's a plot of what WISE actually has mapped out. Now, before anyone wonders, this hole here is just because we haven't finished processing the data. It will get filled in. But clear, very clear. The main belt is right here. Jupiter is right here. And so you can see the Greeks here and the Trojans here. All the red objects, which are scattered throughout, are called near-Earth asteroids. Now, some of them don't look very near Earth, but that's only because that's their static position. Near Earth means its orbit at some point will bring it close to Earth. And we've discovered a large number of near-Earth asteroids. None that we know of yet that are going to hit us on the head. So let's move from our own solar system out to the Milky Way galaxy. Thor's helmet is a nebula in the Milky Way. The star in the center of this particular nebula has 200,000 times the brightness of our own star. This is a visible light photo taken by one of our graduate students out in a little telescope out in his backyard last summer. And it turned out he took this in a place that I thought was that overlapped a very beautiful nebula, so I thought it made a good comparison. It's called the Heart and Soul Nebula. This is the Heart and Soul Nebula in visible light from an amateur telescope on the ground. And here's the Heart and Soul Nebula as shown by WISE. Star clusters. This picture is interesting because it shows not only star clusters within the Milky Way galaxy, right here, but also far away in a complete different galaxy. Brown dwarfs. We expected to find brown dwarfs. We're sensitive to infrared light. We can see them, which visible telescopes can't. This was our first brown dwarf discovered. I realize it's not a very exciting picture, but it turns out when you go through all the calculations of how these images are made, that brown dwarfs, if they're out there, will show up as a green dot. So we were pretty excited when we saw this little green dot. Now these are stars that are a long way, in many cases, in this case, it's quite a ways away, so we can't produce an image that looks, has a lot of diameter to it. All we can see is that it's there, but it was the first brown dwarf that we discovered. Now, brown dwarfs are very cool. In fact, they're so cool you can't see them. This one is so cool that the surface of this star is about right for baking cookies. And so you've got a whole, if you imagine how hot our sun is compared to this. This is an interesting image of nebula in Orion's belt. We actually looked at Orion's belt twice because in 6 months we'd covered the sky, and we're doing it a second time now. But the first time we saw Orion's belt, when we were completely cold, it was so bright it saturated us. The picture's lousy because the camera was blinded. But after we ran out of cryogen and we started to warm up, and as we continued to orbit, our sensitivity is starting to drop. Our cameras are not as sensitive as they were the first orbit. They're still working very well, but they don't detect light as well. That actually helped here because it brought this nebula out of saturation. Since we're no longer sensitive, this nebula no longer saturated our cameras, and we got this image. Planetary nebula in visible and in infrared, again showing how radically different things look in infrared. And now let's move from the Milky Way galaxy out to the whole broader universe. The small Magellanic Cloud is a small galaxy you can see if you're in the southern hemisphere. The first written record of anyone seeing it was Magellan on his voyage around the world. Again, you can't see it from the northern hemisphere, but I'm sure people had observed it long before Magellan got there. These are a series of 4 galaxies that just happen to be fairly close to the Milky Way galaxy. The hidden galaxy is an interesting one because you can't see it invisible, not because it's not bright enough, but because it is behind the dust of our own Milky Way galaxy. The dust of the Milky Way obscures it, but the infrared light penetrates the dust better than the visible light does, so we can see it in the infrared. Sculptor Galaxy, and another example of the false coloring we do, bands 1 and 2, 3 and 4, and then the combined image. And probably my favorite image that WISE has returned is the next few. The Andromeda Galaxy. So it's the closest very large galaxy to the Milky Way. This shows band 1 only. Band 1 is the one closest to visible light. It tends to show the things that are the hottest in the galaxy. In this case, it's the old star population of the galaxy, are what you see in this picture. If we go out to bands 3 and 4, are the farthest from visible light, and they tend to show the coldest stuff. In this case, it's the dust, the interstellar dust, between all the stars within the Andromeda Galaxy. And when you combine all the pictures, all the colors together, you get the composite of the Andromeda Galaxy. I'll actually point out there's 3 galaxies here. There's the Andromeda Galaxy here. There's a little galaxy further away down here. But there's a third galaxy right here that actually is colliding with the Andromeda Galaxy. Those 2 galaxies are in collision right now. So, WISE statistics so far. Now, the WISE mission comes to an end at the end of this month, but that is in terms of operating the instrument. We're going to shut the instrument down after the end of January. But the data processing lags far behind that. We have at least another year of processing all the data, so these statistics actually are going to continue to grow for at least another year. We've taken about 2.6 million pictures. Each picture has 4 colors in it, so 4 cameras, so it's really about 9 million images. We've discovered 34,000 asteroids out of the 150-some thousand that we've actually seen. We've discovered 131 near-Earth objects. Those are primarily asteroids whose orbits will come close to Earth at some point. 20 of the ones we've seen are potentially hazardous, meaning NASA will be tracking them to see how close the orbits will come. We've discovered 17 comets. We've taken another 3 objects up there that were thought to be asteroids and shown that, in fact, they are comets. The difference being a comet has a tail, in simple terms. We've so far discovered 43 ultraluminous infrared galaxies. Those are some of the farthest objects in the universe. And we have verified the discovery of 83 brown dwarfs. That's at least 10 times more than were known prior to WISE. And we've got 500 more candidates we're trying to follow up. We're working to follow up. WISE has been a highly successful mission, both technically and programmatically. Total cost of the mission, NASA's cost, is $300 million. We spent about $76 million up at Utah State University building the science instrument. The GAO puts out a report each year on the performance of NASA programs, and this year's GAO report listed 19 programs, and WISE was the only program that got a passing grade. We actually delivered WISE on time, and so close to being on budget that, for all intents and purposes, we did it on budget. It was a technical success. The instrument has worked flawlessly on orbit. I've been doing this for 24 years now, and I've never had a mission with as few glitches during its operational life as WISE has had. And I really am quite proud of the fact that little old Utah State University in northern Utah has built an instrument that will have an impact on the astrophysics community worldwide, not only today, but for decades to come. We've gotten a lot of recognition from the WISE mission. We've been published in many newspapers. We've been on all the major networks. We've been in some of the magazines that you certainly have heard of, and probably a few like the La Tribuna in Honduras you haven't heard of. So we've had an active outreach program throughout the whole program, and we reached many thousands of students of all grade levels from grade school up through graduate level, and run a number of workshops for a number of different community organizations. Of course, all this was done at SDL. We're up at USU. SDL, Space Dynamics Lab at USU, we had over 500 missions. In fact, we've flown more missions in space than any other university in the world. And WISE is of course, one of those. It takes a lot to do a mission like this. Many hundreds of people involved. But we were very fortunate on the WISE mission. We had an excellent science team to work with. We also had an excellent management team at the Jet Propulsion Laboratory. It's one of the finest NASA teams I've worked with personally in my career. About 30 people at SDL worked full-time on building this instrument, and probably over 100, I'm sure, of other SDL employees contributed a few weeks here or a few months there in getting this instrument built. And we had some great subcontractors as well, and I had a lot of help pulling all these images and statistics together. So what's next? Well, WISE, as important and big as it was, is not all of SDL. We have a lot of major programs, we have a lot of work going on, and we hope our next major program, we hope, rather than looking out to space, we're going to be looking back to the Earth. We're partnering with a commercial firm to try to develop the next generation of weather satellites, and using some of the expertise we have at SDL to develop technology that will be very beneficial in weather prediction and climate and weather. Any images you saw today, you can get your own copies if you're interested from that website that's shown there. And I think that's all I have, so thank you for your time. Two ways. You put a filter in front of it that blocks the ones you don't want, or you pick a camera material that's sensitive only to certain light. Your digital camera in your cell phone is built with a silicon sensor. It doesn't detect anything in the infrared. Well, we do the opposite. We pick materials that are sensitive to infrared light but just don't happen to respond to visible light. Thank you. Okay? Yes?
Do you block out and isolate a certain depth of field, or is it infinity?
Infinity. There's no control over depth of field. The only control is you can't get too close, but if anything is close enough to be out of focus, we're in deep trouble. So, yes?
Does the equipment generate heat? I'm curious why you have to keep something cold that's in space.
Well, several reasons. You've got a big heat generator up there. It's called the sun. Right. So you've got a huge amount of heat coming at you. And although we do try to radiate as much heat to space out the aperture, you can't get it down as cold as we need without going to hydrogen. Matter of fact, now that we've run out of the hydrogen, we ran at about 17 Kelvin. It's now warmed up and it's stabilized at about 70 Kelvin, 70. And I can't tell you off the top of my head what that is in Fahrenheit, but it's probably around minus 320, 330 Fahrenheit. and that's where it's equilibrated. So if we could have taken all those pictures at that temperature, we wouldn't have had to go all the work putting hydrogen. But we wanted to be more sensitive, so we had to use the hydrogen to get even colder. Yes?
I understand that WISE looked at perpendicular line from the Earth-Sun line.
Yes.
What was the rationale behind that?
It was the two things. One is we needed to have an orbit which gave us all sky coverage in some by using some repetitive pattern. And by looking directly away from the sun, if the sun's that way, we look this way, we were able to shield ourselves best from the sun's rays glinting into the aperture. If you had an orbit that looked away from the sun, the opposite side of Earth, sooner or later the orbit would bring you to look to the sun. So it was the best compromise in the orbital constraints. Yes?
What are the keys to staying on time and on budget?
Well, I'm sure that some of the guys that worked for me would give you an opinion about that wouldn't be very flattering to me. But I have a term I use that I was actually taught by the JPL program manager. It's called looking over the horizon. My job as the program manager was to always be looking 3 to 6 months ahead and looking for problems and solve them before they became big. There's my management philosophy in a nutshell. Yes?
Are there any other colors for the cameras that you could have used that would have revealed other objects?
Yeah, actually the 4 colors selected were very specifically tuned for the objects that we found. Brown dwarfs, bands 1 and 2 were tuned very carefully for brown dwarf detection. Bands 3 and 4 were for the far universe. Depending on whose astrophysics was of interest, if you got a different group of astrophysicists interested in certain other phenomenology, you probably would have tuned those cameras to different colors. So that was they were very carefully picked for the particular science it was designed to do. So, yes?
Some of the spiral galaxies that you showed look very similar to hurricane cloud formations on Earth, and yet they're in very different environments. Can you say anything about the physics that creates that?
Well, I'm neither an astrophysicist nor a climatologist, so I probably should choose not to answer that. I don't know. I mean, in terms of the spiral galaxies, it's gravitational. We know that, of course, because of the distances involved. I can't address the hurricanes at all. Yes?
So after the mission, will the light be recovered, or what will happen?
No, just like any satellite up there, it would cost you far more to try to get it back than it would ever be worth. It costs you $1 billion to send the space shuttle up to get it, and it costs $300 million to build it. So we're going to put it into a quiet state, and it will continue to orbit. Actually, the onboard computers will continue to work and keep the solar panel pointed to the sun. The reason we're shutting off on this January 31st is a word many people here don't understand. It's called funding. NASA is ending our funding to operate. But we're putting it into a self-controlled mode where it is safe. And if the scientists, a number of the astrophysicists are currently writing proposals to NASA to get more funding. And should they accomplish that, we can wake it back up. About 20 to 25 years from now, it will re-enter the atmosphere and burn up. So.
John?
Yes.
Where were the cameras themselves made?
There were 2 types of cameras. The 2 short band cameras were made by Teledyne Sensor Systems in Camarillo, California. The 2 long bands were made by DRS Systems in Los Angeles. They were the long wave cameras were custom built for this instrument. That's a technology which was developed during the 70s and 80s, and it's sad, but our country's losing the technology. There's no one out there buying that kind of camera anymore. And so we were glad to be able to buy 2 of them from DRS to try to keep this technology within the country. So, yes?
Last question. What's the future for infrared astronomy? Is there going to be another space-based infrared telescope at greater resolutions or different wavelengths?
The next step, NASA gets far more proposals than it will ever be able to fund. And there's a lot that are being proposed. The next big one, though, is the James Webb Space Telescope. It's a instrument that's currently being built. Whereas WISE was $300 million, and I know that's a big number, but in NASA world it's not. James Webb is more than 10 times that cost. But James Webb is an infrared telescope. But unlike WISE, with a wide field of view to survey the whole sky, James Webb is a pointed instrument. And so it will go up. One of the primary drivers to fly WISE was to build this all-sky catalog so that when James Webb gets up there, it has a catalog of objects to go look at.
John has assured me that he'll stick around. Some of you may have additional questions, and you might just want to meet face-to-face a person that's had such a connection to something so amazing. To think about these images that we've seen. Will you join me in thanking John for the presentation?